Okay, welcome back. It's time to talk about bond order because I finally learned what it was. And it's actually not that hard. It's just kind of like the the length of a bond between within a molecule. So, a bond is, as we've established before, when you have two atoms and they are connected. They can have a single bond, they can have a double bond, they can have a triple bond. Probably not more than that because that's when it starts to get really weird. But these bonds will have definitive lengths. We don't really get into like the deep parts of that, but depending on how many of these bonds there are, like single bond or double bond, the length will be different. The general principle here is that the more bonds it has, that's the more attraction it has. Uh, I take that back. Uh, it was true, but not what I wanted to say. The general rule is that the more attraction there is, the shorter the bond is going to be, which means when there are more bonds, they're going to be pulling each other tighter and tighter, so they'll be contracting even more. Same goes for when they're small. When they're really small, atoms, they will pull together stronger than bigger ones. So bigger ones only have like a tiny or a really long bond length because they're not pulling each other as strongly. And finally, in terms of that, the more polar it is, the more stronger they're going to pull. So if it's a plus versus a negative, these bad boys are going to be pulling on each other so hard that they're going to end up really close together. Yeah, so that's just kind of how you determine the bond length of them. Let me check this. So resonance structures do kind of tie into this. I think you have to tie in when you're calculating bond length. But it goes like that. So, uh, yeah, so sometimes the bond lengths can be in between like specific values. So the values of 1, 2, and 3 for bond order. Bond order is kind of how long it is. You calculate bond order by looking back at my notes. Okay, you calculate bond order by how many bonds it has. So if it has one bond, it is bond order one, bond order one. If it has two, bond order two, and if it has three, it's going to be bond order three. When it starts getting weird is when you tie in other factors like how many bonds there are. So if we only have like a single atom, or two atoms connected by a single bond, we have bond order one. But what if you have three? What is the bond order here? So the way you calculate that, or let's see, well, that, like, that's the resonance structure. So if resonance exists, uh, resonance shows one double bond. No, what is it? One double bond spread over three positions. Yeah, so that's for resonance. But if you have a certain amount of bonds, then the way you calculate it is by the amount of pairs over positions, I think. What is it? Let me think about this harder. Uh, I think it's just basically that. Like, you have one, you can bundle to one, but when you have multiple pairs, you have over positions, um, which would, if it's like this, it would be normal, like two, two bonds over two positions, uh, or four, technically four bonds over two positions. Yeah, so one, two, three, four for two positions to get you bond order two, and I mean, it just goes back to like we have two double bonds, so it averages out. If that makes sense. So when it gets into resonance, it would be like, hey, it could be in either one. So you have how many pairs? I think it would be. I'm gonna look at ChatGPT. One double bond over two positions, three positions. Oh yeah, so one double bond over two positions would be one half. So that means that the bond order here would be one half, if I'm not wrong. I believe that's it. So that's what bond order is. The more traction there is, the shorter the bond is gonna be. Uh, and yeah, anyways, I'm gonna pause it because I think that's it. But I'll be back. Yep. So just to reiterate, now that I'm completely sure of it, the way it goes is the amount of bonds, oh, not necessarily pairs, like the literal amount of lines that you've drawn, bonds over the amount of positions there are. So like this is a position and this is a position because just like the space between two atoms, and that's how you actually calculate it for any bond length. Then you get the bond order, and a higher bond order is a shorter length. Um, I hope that's intuitive. For example, we have NO3 right here, which is one, two, three, four bonds over one, two, three bond locations. Is going to have a bond length of 4/3 or 1.33. It's not too hard. That's about as complex as it gets.